Hello? I have no idea if it's working. Hello? I have no idea if it's working. Oh, it looks like it's working. Okay. Let me pop some music on. Um, we'll just put some music on and then we'll do some math problems here. Oh. Oh yeah. Oh yeah. This is good. All right. Let me. I forgot how to live stream completely. The nice thing is, I think that all of my old viewers, if I have any, um, don't follow me anymore. I don't want to put this over here. I want this like this. Oh yeah. Oh yeah. We're cooking. We're so cooking. Just give me like 30 more minutes to figure out where. Oh yeah. Oh yeah. Okay, so now we're gonna be discussing the topological properties of the graphs of the following Markov chains. And you might be like, wow, what the hell is a topological property of one of the graphs of the Markov chains? And that's referring to irreducibility. Oh yeah. Or however you spell it, which I'll define in a second for you guys. But it's also asking about being aperiodic. Which I'll also define. So basically, irreducibility is going to be talking about. That music's probably a little too loud. At least on my side, it is. Okay. Yeah. Okay. So irreducibility just means that I can get from any state to another state. So let's say I have a case where I'm a little frog. I can't really draw a frog very well, but I'm gonna darn try. Here's my little frog, ugly as hell, beautiful frog. I mean, oh yeah. Wait, let me give him some eyes. And he wants to jump from state to state. And let's say there's some chance he jumps to this state, this lily pad over here. But once he's over on this lily pad, there's also some chance he jumps over on this lily pad. But then there's also some chance he stays on the lily pad. And then there's also some chance he stays on this lily pad when he's over here. Okay, so this is the graph they're talking about. But what is irreducibility asking, you might say? Well, what irreducibility is asking is if you can get to the other state from any state. Let's say this guy couldn't. Oh, give me a second. Oh, once he's over on this lily pad, he's stuck. He can't get over on this one. That means that it's not irreducible. It means that you can't get to every state. So, in this case, if we had something like this, lily pad A, lily pad B, once you're on B, you can't get back over onto lily pad A, so it is not irreducible. Now, aperiodic is just talking about return time, basically. So if I'm on lily pad A, I want to know, let's say this is lily pad B and this is lily pad C. I'll label them for you guys. I want to know about jumping. I want to be jumping between lily pads, right? So if I'm here on A, I want to know how long would it take me to get back to lily pad A. Is it going to be, or I'll take C away, it's really not necessary for this. If I have to jump this way, and I have to jump this way every time, 100% chance, when you're on the other lily pad, you always jump and you always jump to the other one. Well, to get back to A is going to take me 1 step, 2 steps, and then every time to get back to A, or it could take me 1, 2, 3, 4. And aperiodic means you don't want like the greatest common denominator, so the factor that goes into it, to repeat. So now let's determine some of these for these problems. Oh dear, I didn't mean to do that. You gotta be careful, can't delete that. Okay, so we're gonna do for problem A. So we're gonna first model this because that's probably the easiest way to do it. And since there are two states, you can see because we're adding up the rows. This is like A, this is like saying there's lily pad A, and this is like saying there's lily pad B. They don't need to be lily pads, but we like to draw them as nodes. Oh dear, what happened? I can't see things. I don't know what's happening. I'm just gonna let it cook. Alright, so we have lily pad A, lily pad B. And this is saying, I'm gonna draw this out in a table. So, can you guys see? Yeah, you can. We have state 1 and state 2, state 1 and state 2. This one's gonna be 1 and this one's gonna be 2. If we're on state 1, there's a 50% chance we're going to stay on state 1. So I draw a guy like this, and I give it that 0.5. And then state 2, I guess I can copy these over so you guys can see better. And now if you're in state, or we'll stay here. So you're in state 1 again. There's a 50% chance you're going to go to state 2. So I write this with the arrow, 0.5. Now, if you start in state 2, there's going to be a 50% chance that I stay, or I go to state 1, seen here in this box right there. So I draw a little arrow, I go 0.5. And then if you're in state 2, there's a 50% chance you stay in state 2. So I draw this here, I have a 0.5. Okay, now we want to answer some questions about whether it's irreducible and whether it's aperiodic. So to do that, we're going to be like, can I get to every other state from any starting state? Well, yeah, clearly I can. You might not get there immediately if you get really unlucky, but you can. So it is irreducible. Alright, but now we wonder, aperiodic, huh? Well, let's take a second and think about this. So I can get over 1, and then I can get over 2, and since returning from this state and getting back to this state could be any number. It could be 1, could be 2, could be 3, could be 4, 5, 6, 7. There's no like common factor. So the greatest common denominator of that is 1, which means it is aperiodic. Alright, so now we've done A. So let's move on to B. Just give me a moment to erase all this stuff very carefully. Uh-oh. Can I do it? I got rid of it a little bit. Oh well. Oh no. That race is way too big. What about this guy? Oh. A little smaller. Alright, let's go to B. So now we still have 2 cases. So we're going to have lily pad 1, lily pad 2. I should make them green if I'm going to call them a lily pad, shouldn't I? Lily pad 1, lily pad 2. And we're going to draw this guy out because it just kind of helps. Let's see. So if you're in state 1, there's a 50% chance you're going to stay in state 1. So we draw it like this. And then if you're in state 2, is going to be a 50% chance that you go to state 1. If you're in state 1, there's going to be pardon me. Am I misreading this? If you're in state 2, 0% chance of going to state 2. So this is 1, so I misspoke. Which means that, well, to see the rest of the probability, like if you're in state 1 and you're starting and you're going to 2, what am I doing wrong? Oh dear. Dear, oh dear. Let me think for a moment. One. Like that. Yeah, that should be right for this one here. Because you have, if you're in state 1, 50% chance you go to state 1 again. If you start in state 2, 100% chance you go to state 1. Does that make sense? I should be reading it this way. If you're in state 1, 50% chance you go to state 1. If you're in state 1, there's also 50% chance you go to state 2. If you're in state 2, 100% chance you go to state 1. 0% chance you stay here. So I was just reading it wrong. You want to read it by the rows again. Unfortunately, there's like a lot of, like half the textbooks use rows, half the textbooks use columns, so it makes it very confusing. So is it irreducible? Can we get to every state? Yes, pretty clearly we can get to every state. Now the question is it aperiodic? Well, let's see. I can get to myself from this state, so that's 1. And then, but I can't get back to myself from this state. But does that matter? Because 1, and then I guess I could get 1, 2, but I could also have 1, 2, 3, or 1, 2, 3, 4, or 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So as you can see, the greatest common denominator of any return state is going to be 1 for each path. So since it's 1, it is aperiodic because the GCD of the return state. You can say GCD of, kind of do this fancy T, quite like it, equals 1. So yes. Yes. A fun yes, why not? Alright, let's move on to the next problem. I'll cross this one out in red. So fun to erase all this stuff. Oh, I don't know. I'm getting rid of that. I need that. Haha. My bad. So I don't remember it being that hard to erase. Alright, let's do the next one now. I'm not gonna write out all the stuff I was writing down before but I will draw it out because I think drawing it makes it quite nice. So if you're starting in 1, there's 1/3 chance you stay in yourself. So we say 1/3. And now there's a 0% chance I'm going to go to B, but there's a 2/3 chance that I'm jumping all the way here. Okay. If I'm starting in 2, there's a 0% chance that I'm going to go to 1, and there's a 100% chance I'm going to myself. If I'm starting in 3, there's a 0% chance I'm going to 1. So 1/5 chance that I'm going to go over here. There's a 4/5 chance that I'm going to go here. So now we want to know, is it irreducible and is it aperiodic? So we want to see, can it get to every state from every starting state? Can you get anywhere? Are you going to get stuck anywhere? And the answer is, once we go to B, we're going to get stuck. See, if I'm in B, or I start from B, or if I even get to B at any time, I can never get out of it. I have a 100% chance of just looping in myself. So it is not irreducible. No. This is our first no, which is kind of exciting. However, now we want to think about what's the greatest common denominator of getting back to yourself. Well, we see if you start here, 1, 1, 1, 1, 1, or 1, 2, you can just kind of count up like that. So that works out fine. Here, you can get back to yourself. You can always get back to yourself in 1, which means the greatest common denominator for any state is going to be 1. So remember, when we have that GCD is equal to 1, then we can just say, yes, it is aperiodic. Alright, so that one was not bad at all, even though it's a big boy. So let me just erase all this stuff again. Alright, let's do this next one. So, we're going to have just 2 lily pads again, and then this one, if you start in state 1, there's a 100% chance I go over here. If I start in state 2, there's a 100% chance I go to the first one. Alright, so now let's talk about this. Can you get to every state from every starting state? Well, yes, pretty clearly. I can get here to here to here to here no matter what. It's never going to be a problem. So irreducible, yes. Now the next question is like, how long does it take to get to each state from each state? Well, let's say we want to go from A to A, and you can pass through A many times. So let's make some tallies. So A will take 1, 2. So the first one, we say 2. And then A could also take 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And if you don't see the pattern, it's just going to be 2, 4, 6, 8, 2n, 2n times to go through, which means also, if you start from B, it's going to be the same thing. I start from B, I go 1, 2, 3, 4, 5, 6. It's always going to be even number. So since The greatest common denominator of return walks is not 1, since we say GCD is not 1. It is not aperiodic. No. Nope, there's a little bit there. Alright, so in this one we have 3 again. We have a 1/2 chance, a 50% chance that it stays in itself. Little greedy guy there. We have a 1/2 chance that it goes to this node. Starting from the second node, 0% chance it goes here, 50% chance it stays in itself like a greedy bastard. 50% chance it goes over here. For this one, it has a 1/3 chance of I guess I'll start in order. 1/3 chance going here. Gonna have a 1/3 chance here, and then it's going to have a 1/3 chance going here. So irreducible, can get to every state from any state, never gets stuck in itself. Yes. And then the quick way of just telling if it's aperiodic is, since it can go into itself, each of the nodes can go into itself. Well, yeah, then it's going to be aperiodic because it will just be 1. Hello, Noah PB. How's it going? Alright, so pretty easy. Now I just need to pull up some more problems to do. Maybe we'll do some non-Markov stuff. But we will see. Or maybe we'll do a Markov problem. Let's see. Let me find another problem from the book. I guess I can steal one from class. Yeah, sure, I'll do that. Give me one moment here. All right. Let's see. Hopefully you guys can see that on there. I just got to zoom in some and adjust it for you guys. Make the problem a little smaller so that we can see everything. Hello, Foxy girl. I haven't seen you in forever. How's it going? Alright, let's see. Quality of that will get a little bit better, probably. Okay, so we have a mouse trap in a room, and we wanna model this with a Markov chain. So you might be like, wow, how the hell are we going to do this, right? Let's first read the problem before we go into any existential crises. So we say a mousetrap is placed in a room, in room 1 of the house with a pictured floor plan. Each time the mouse comes into room 1, he is trapped with a probability of p equals 0.1. If he is not trapped, he leaves each room by one of its exits, chosen at random. Model the path of the mouse through the house as a Markov chain. I've been doing pretty well, Foxy. I'm studying math, if that wasn't clear from the video. Actually, how far can I? Okay, you guys can see it until about here. I'm making a little mark so I don't like go off screen accidentally, because that would be really unfortunate. This is Markov chains. They're pretty useful, I'd say. I don't know. I find them interesting. I just worked on a project with them, so they're pretty useful for a lot of things in computer science and a bunch of other topics. So, how are we going to model this, right? So we have a bunch of different places. We could be in room 1, 2, 3, 4, 5, 6, 7, 8, or 9. But there's another room that we got to consider, right? There's the trapped room. You could get trapped, and once you're trapped, as the problem states, you can't leave. I don't know how useful this topic will be until, like, for... I mean, I don't know where you are for computer science. It's useful if you continue studying computer science. Okay, so we're gonna model one of them by T. We want to know the trap state, and then we want 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh dear, this is going to be quite ugly, isn't it? Odd a little. Oh god. What's wrong with your mouse is so terribly difficult. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 rooms and the trap state. So hopefully I'll just draw out a few of these. We're going to not probably do all of it, right? But if you're in the trap state, there's a 100% chance you're going to be in the trap state for the next, and then you're going to have a bunch of zeros. Because remember, each row needs to add to 1 in terms of the probability. So, bunch of zeros here. 1, 0, 0, 0, 0. Now, if we're in 1, there's going to be... If you're in room 1, if the mouse comes into room 1, let's see. Actually, it's each time he comes into room 1. Let's see, each time the mouse comes into room 1, he is trapped with a probability of that. So if he's not actually coming into it for the first time, then we don't even need to care about this. We can actually just say, when he's in room 1, he has a 50-50 chance of leaving, because it's only when he's coming in that there's a chance that he's going to get trapped. So, there's a 0% chance if he's in room 1 that he's going to get trapped. Because it's only when he's coming into the room that he might get trapped. But now there's a 50-50 chance he goes to 2 or 3. So, 0.5, 0.5. Rest is 0. I'll just do ... because I'm lazy. And now, if he's in room 2, he has to go into room 1, right? But when he enters room 1, each time he comes into room 1, there's a 0.1 probability that he is going to get trapped. So we write 0.1. And then the rest of it is just that he's going to be in a normal state, not trapped in room 1. Then we write 0, ... because this already adds to 1. And now we're going to consider, what if the mouse starts in room 3? Okay, well, if he enters room 1... So actually, let's see. There's a few different interpretations of this problem, but I'm going to continue interpreting it in the way that I've been interpreting it. Let's see. I think I'm interpreting it wrong, actually. Oh dear, no, I did not mean to do that. How big is the... Let's take a step back and think about it a second longer before I jump to conclusions about how the trap works. He's trapped. He's 0.45 for room 3 if that were the case. Yeah, but let's see, I'm trying to think about it because it's dependent on whether you go into room 1, right? So it's each time the mouse comes into room 1, so you have to be in room 1. I've gotten myself all confused. This is interesting now. Well, if you're in room 1, is the way you think about it, you have a 0.1 chance of getting trapped now. I think that's because the chance you go into room 1 is going to be, in the case of being in room 2, starting in room 2, is going to be 100%. So it's 0.1 that you get trapped when you're leaving. We can think about it not as leaving, but since time is jumping in the way it is, you can, once you're in the room, we can consider the probability of getting trapped. So this is actually 0.1. If you're in room 1, you have 0.1, and then you have 0.45 for going into room 2, and 0.45 to go into room 3. 0 ... And now 2, it's a 100% chance you go into the room. Do you guys agree? And then 3, you have a 1/4 chance of going into 1. Oh, okay. Okay, here I'll re-explain. So we decided that okay. We decided that if you're in room 1, that's when you should calculate the trapped chance of becoming trapped, because when you're in room 2, there's a 100% chance you go into room 1, and since time is jumping here, it's not continuous. We don't need to care about which side. Well, it matters which side we do it, but it shouldn't be as you're coming into the room. It's like once you're already in the room, the probability of getting trapped. So 1/4 chance you go to 1. Some zeros here. 4 has 1/4. 5 has 1/4. 6 has 1/4. 0 ... If you're in room 4, 100% chance you go into 3. Rest is 0. 500% chance you go into 3. It's getting very messy, sorry. I'll clean that up. Now 6, 50-50 that you go into 3 or 7. Pardon me? 6? If you start in room 6? Or from which room are you starting in? Is there 5 places I can go? If I start in room 3, there's only 1, 2, 3, 4 with a 1/4 probability. And since we're considering the trap in, like, you can only get trapped from the first room, there's only 4 places I can go. So there's a I can't stay in the same room, I don't think. Yeah, because he leaves each room. I don't think he stays in the same room. So I think this is right. We have zeros in here, but I'm kind of lazy, so I'm just going to do ... In 6? In 6, there's 5 places to go to. I think from 6 I can only go out this door or out this door. Yeah, in 6 I can only go out these 2 doors. I can either go 50% chance I move to room 7, 50% chance I move to room 3. No, you're all good, Foxy, don't worry. 7, there's a 1/3 chance I go to 6. 1/3 chance I go to 8. 1/3 chance I go to 9. Rest is 0. And then 8, 100% chance I go to 7. 9, 100% chance I go to 7. So we have some zeros that I am way too lazy to fill out. But you kind of get the idea. So that's kind of an interesting problem. And this is a Markov chain, so we can run it through a simulation. If we make this a matrix, call this matrix P, and then we say, I'm going to start in 1, 0. So, well, it would be 1, 0, actually that's saying I'm starting in the trap state. That's boring. Pardon me. And then we're going to have, this is 1, 2, 3, 4. So we have 6 more zeros. 6 more zeros. And this means I'm starting in room 1. And I want to see how long it would take me to become trapped. And basically, I can run this through a computer. It can do a lot of work for me. And I can figure out how long it would take for me to get trapped, or if I get trapped, however frequently with each move. And one of the really nice things about Markov chains is it forgets everything, so it has no memory, which is what this what this property means. So if that was P, we could say we have V times a matrix is going to be equal to, I'll call this V0, is going to be equal to V1. And then we say V1, which is the next step, times P, is going to be equal to V2. ... Which I think is really cool. You can do a lot of stuff with Markov chains. I'll try and find another application from the book here, and hopefully we can do some more stuff with them. Let's see. I guess we can talk about a steady state vector. And you might be like, what the heck is a steady state vector? And I'll explain it in 2 ways. In the first way, I'll explain it in the sense of linear algebra. and then I'll try and explain some intuition behind it. So a steady state vector is just when we have some vector, we call it pi or something, times our matrix, times our Markov chain, and it's going to be equal to that same vector pi. And if you know linear algebra, you'll probably be like, wow, that just looks like an eigenvector. And that's where you're absolutely right. We can essentially say this. And of course, if you know linear algebra, you can be like, wow, I can solve this really easily. This is not very interesting. Yeah, sure. And now we kind of wonder, what does it mean in the context of a Markov chain? So in the context of a Markov chain, let's go to back to that very simple starting place where we have two lily pads and we're jumping in between them. We can jump in between these lily pads, and we want to model this. And maybe I jump onto the same lily pad. And we kind of wonder, well, is there any time where I would get to a state where I'm not going to ever get out of this state? Let's say I have I guess a 100% chance of jumping there. Actually, no. Here, I'll give a better example. Sorry, it's hard to come up with examples on the spot, but it's kind of fun. 100% chance I jump back onto here, but there's a 50% chance that B will go from here to jump onto A, and there's a 50% chance that it jumps onto itself. So say I'm a little frog jumping around. 100%, if I'm on lily pad A, 100% chance I jump back to lily pad A. If I start on lily pad B, 50% chance I jump over here, 50% chance that I jump onto myself, right? And what you're kind of curious about, if we model this as a matrix P, we want to know, is there some state we can start from, or any state that we'll just get stuck in indefinitely? And in this case, it's super simple, because if we know we start on A, or if we ever get to A, we're just going to be going back to A, and you're on A, you're on A, you're on A, which essentially means that the vector is just going to be 1, 0 for forever. So there's a pretty clear answer to this one. Unfortunately, a lot of other cases you're going to need linear algebra to solve for these states. So let's say we have P is equal to what should we do? 0.4, 0.6, 0.5, 0.5, like that. And we want to solve for our steady state. So we take 0.4 minus lambda. We're taking the determinant of this, by the way, because that's how you solve for it in linear algebra. And then we take 0.5 minus lambda, and then we say minus 0.5, 0.6. All right. I think I'm going to end stream, guys. Thanks for coming in.